So the idea here is of today's call is to have 5 presenters, giving them allowing them a brief introduction or brief comments on the topics that they focus on, and then we would like to hear from others if they have anything else to say to whatever the presenters are going to say. And we're going to start sort of with few more general topics, and then we'll focus more on details of and programming and things like that. So we'll start with Brad Milash, my colleague from CHPC at the University of Utah, who's our bioinformatics expert, and he will give us some basic ideas that he has about how to work with big bioinformatics data.
All right, thanks, Martin. Thanks very much. Yeah, as Martin said, I'm a bioinformatics expert with the Center for High Performance Computing in the University of Utah. And I work with bioinformatics scientists and biologists across campus who are trying to process large bioinformatics data sets. And so I'd like to discuss a few considerations on how to handle those data sets. I don't have slides for you. All of my notes are in the call document, so feel free to take a look there at what I'm going to discuss. And so here are a few considerations for dealing with bioinformatics data. The first is the data volume. So we frequently deal with tens, single to many terabytes of data. In a typical bioinformatics analysis or experiment, you might have tens to hundreds of individual samples, each of which has many tens of gigabytes of raw data. And so that very rapidly comes to terabytes of raw data that you need to deal with. And so why is there so much data in these experiments? Well, there are errors in the raw data. The typical error rate off of the genome sequencer is in the range of 1%. And so when you look at a particular piece of DNA, you need to look at that DNA multiple times with multiple independent observations to be certain that the features that you see there are for real and are not simply errors. And there are also cases where you're looking for very rare events in the genome or in a sample. So in the case of cancer research, all the cells within a tissue sample that you're looking at have slightly different genomes. Some of those might have very rare but very important mutations that you want to see. But the mutation rate can be down as low as the error rate in the genome sequence data you're getting. And so you need to sequence very, very deeply, and therefore you get lots and lots of data to look for these rare events. And so a serious consideration is storage of all this data. And you can store these data at places like Amazon and whatnot, but it's really useful to know just what data volume you're going to be faced with. And so, so long term, it's incredibly useful to create a data management plan. This is a foreign concept to some scientists, but it's an incredibly useful tool just to figure out, how much data will I have? And also in the short term, what is the high watermark for the data that I have? So in these analyses, there's typically an overall reduction of data, but to get there, there's a certain amount of data bloat. And so you need to get past this high watermark in order to achieve that result in your data reduction. So you need to figure out, are there intermediate data files that you'll be producing? Does the data need to be uncompressed just to process it, or can you just stream compressed data into the analysis software you're working with? And it's incredibly useful to do some benchmarking with some smaller data sets to figure out, how does the data behave and the data volume change over the course of the analysis that you're doing. And then in terms of computational optimization, lots of the bioinformatics software we use is limited by the memory on the machine or by the I/O to the disk or the network. It's not like other sorts of modeling or simulation where you're really limited by raw CPU power. And so in many cases, when you're running on the finite nodes that we have on our clusters, you're really limited by RAM or I/O, not by the CPU at all. And so you will find that trying to pack more and more tasks onto a node on the cluster actually slows things down. And it's incredibly useful to perform benchmarking, again, with the data that you have, with the particular genome of the organism that you're working with, to try to optimize how well does a particular piece of software work on a particular piece of hardware that you're working with in your HPC environment. So that benchmarking up front is really critical. These systems tend to be, these softwares tend to be limited by the I/O that you have. And so high performance file systems like Lustre are incredibly valuable. So whether that's just a partition, a scratch space that you can use or something like that, definitely take advantage of those, or lobby to have those things created at the center where you're working. And so the last main topic I'd like to discuss is the use of workflow managers for these analyses. So very few bioinformatic codes or softwares use message passing internally. So MPI is a very rare thing in the bioinformatics world. And this means you're really limited to doing single node jobs within a bioinformatics analysis. I was in a meeting with colleagues and some data scientists in different fields, and some of them were astonished that we don't do multi-node jobs in our work. And, but single node jobs are really sort of our bread and butter. And so the workflows that we run are composed of dozens or many dozens of single node jobs. And if you consider the analogy of compiling a piece of software, that might have dozens of independent source files. You would never do that with a simple script or do that manually. You'd use a tool like Make or CMake or something like that. Well, this is really analogous. You're trying to orchestrate many dozens of single node tasks on a cluster to get the final result. These have to run successfully. They have to run in the proper order for this thing to work out properly. And so workflow managers have been created to help bioinformatics analyses by orchestrating these dozens of single node jobs. And so there are lots and lots of choices of workflow managers out there. There's a terrifyingly long list. I have a link there in the notes to a site put together by Paulo Di Tommaso, who's curated a list of well over 100 different workflow manager tools to do this sort of thing. And I found a few that I really like. So two that I really like are SnakeMake and Nextflow. And I provided links to the documentation on those. Both of those are in fairly heavy use at the University of Utah. Things I like about those tools are that neither require sysadmin support. So you can install these yourselves and get started right away. You don't need to wait for someone to install this piece of software for you. Both of these are cluster aware, so they'll work on Slurm clusters, some grid engine clusters, LSF, all kinds of different clustering tools work with these things. And so these tools allow for efficient parallel execution of your tasks. So you can set them up to run any number of parallel tasks at once. They allow for modular workflows and reuse of those modules. So you don't have to rewrite every piece of analysis code from scratch. You can reuse the quality control step from the previous analysis in your next analysis simply by including the appropriate module. And it allows for standardization of your analyses. So if you run a lab or manage a lab, you could mandate that a particular tool be used to run your analyses, and then members of your team can collaborate and share different modules. And finally, it allows you all the good things that come out of modern software engineering, so version control, reuse, things like that. So it's very simple to standardize and reuse analyses that you've used from previous experiments. And so I found these workflow managers incredibly valuable, not just in bioinformatics, but in other endeavors as well. We offer a SnakeMake course a couple times a year that's really gaining traction at Utah. And I think these tools become quite popular as analyses like these take place. So with that, I'll turn it back to Martin. And what, are we taking questions at the end, Martin?
Yes, so we have a few questions in the chat. The first question is with respect to biocodes. What do you do about a lot of small files? I guess my question would be first, how many, or do you have experience with problems or systems where there are many small files? And if you do, how do you go about those?
I haven't run into that personally. I think for storage, I would use the standard tools like tar archives, so tar.gz files, to collect those together for storage purposes, rather than trying to manage millions of tiny files for long-term storage. Short-term, I would imagine those would need to sit on the file system. But for long-term, if you're putting those into Amazon for storage or Google and Glacier or something like that, I would probably tar those together into a single big file.
All right, sounds good. Now let's see. The next one is a lot of bioinfo apps seem to stream their data. Any good ways to split upstream data into chunks for easier parallel processing?
There are limits to how much you can break that up for processing. You know, so a typical analysis in the bioinformatics sense is to take your sequence data and align it to a reference genome for the organism that you're working with. So you take human genome sequence data, align it to the human reference genome, and work with that aligned data at that point. That is certainly something that you could break up into chunks, stream those separate sections, those separate chunks in parallel, and then reassemble the results for processing. And in a case like that, you know, there would be no, you know, it would really just be a matter of how many chunks do you want, right? And break your data set into chunks like those. But inevitably it comes back to, we need to process the data as a whole. And so if you have 100 samples that you're going to break up into little pieces, align them on the cluster and bring the results back, I wonder if you would get the same performance by simply aligning each sample by itself on a node of its own. So it might be interesting to try benchmarking, you know, those two different scenarios and see if you get different results. A lot of the bioinformatic code is really smart about multiple threading, but not about message passing between nodes, right? And so you're still kind of limited to the confines of a single node for doing a piece of work. So whether you're sending chunks of data through there or a single sample through there, at the end of the day, it might be kind of the same.
All right. We have 3 more questions, but we want to make sure we can get everybody, all the speakers covered up. So maybe if you can quickly take a look at the 3 questions there. The first one is DMP tools. So that data management processing tool that I managed to Google up here. They don't say data management plan tools.
Data management plan. I think that's a great place to start for data management. And I would start there. And if that doesn't meet all the, if that doesn't answer the appropriate questions, look elsewhere. But I would start with dmptool.org. That's a great site.
All right, great.
I'm going to transfer questions into the doc and maybe Brett can answer them there so we can move on to our next speaker.
Yeah, that sounds good. So the next one is Jana, and she will talk about their experience with running a genomics cluster at Northwestern University.
Hi, everybody. I'm Jana Nugent. I'm a senior computational biology specialist at Northwestern. We have a genomics compute cluster that's dedicated for genomics research. It's part of our larger cluster. So it's around 2,500 cores. We have about 300 researchers who use it today. And I just wanted to talk about a couple of, so I thought Brett did a fantastic job of overviewing what the challenges are in this arena. One of the interesting things about genomics is it is embarrassingly parallel, which is fantastic. So it's very easy to break up your data and just run everything in a high throughput fashion. One of the pieces that's always hard is moving the data around. So as Brett was talking about, the slowdown isn't the CPU. In fact, for our site, I'd say it's mostly getting data on and off of the cluster. People have massive data sets all the time that need to move. I have a nightmare horror story of somebody who pulled, I think, 130 terabytes from USC to Chicago, and it took over 6 months. So that level of problem, and then locally, right, people have more data than makes sense to store on our high performance compute cluster. So the data needs to go from long-term storage onto our cluster. And if it's a 10 or 20 terabyte chunk, you know, no matter how fast we do the computes, the data flow is just very slow comparatively. We use Globus. There was a question earlier about small file sizes. We definitely see that. One of the things our cluster provides is a scratch space. So that's 180 terabytes of scratch that people, you know, we let people keep data there for 30 days. And it can be at the 30-day mark, somebody can have, you know, literally 65 million files. And so just the maintenance of deleting that many files has an overhead. But regarding transferring small files around, Globus lets you set a certain file size as the default if you do have a Globus server at your institution, and you can tune it for genomics by having the size go a lot lower than what the default is. Wow. So one of the options Globus lets you do is you can have multiple servers, like for large files or small files, if you want to optimize that way. Another thing, we were talking about streaming data. One of the things we're experimenting with is Parabricks, which is something you have to pay for, but that's that lets you do the alignment step on GPUs, and it's providing about a 10 times speed up from traditional CPUs. So that does have a streaming component to it. We're still trying to work out if that 10 times speed up translates when you take into account all the bottlenecks that you can experience downstream of just the compute, so just the data transfer itself. And then finally, I want to just mention that this community, just in working with these researchers, they have so much that they have to learn about their field and their specialization before they even walk through the door about HPC, that I often am helping people who have never done programming, or perhaps even did programming and then realized they really hated it. And then now, like post-COVID, people have to come back into the HPC space because they're not able to work in their labs as much as they had been before. So when the way that plays out is there's a lot of inefficiencies that people build in, and there's a lot of learning curve issues. Oftentimes, as Brett mentioned, our code doesn't run on multiple nodes, but there's a lot of wishful thinking where people will request multiple nodes in the hope that then it will magically go a lot faster. So there has to be, just in terms of helping this community, there has to be some level of making sure that people make good decisions around efficiency and around using this, that they just haven't been trained to use it before. So that's really the overview of this space that I wanted to give today.
All right, great. I don't think we have any major questions on you. So maybe, oh, we have one question here. Do you encourage a standardized, no, sorry, that was for Brett, never mind. Yes, so maybe we'll move on to Mahmoud. And if you guys have any questions for Jana, just put it in the chat.
Actually, I have one quick question, because I think what I think is very interesting for the bioinformatics community is that there's a lot of already pre-packaged software. But I'd like to ask really briefly if either speaker would comment, if people are writing new code with different types of data, what are your recommendations? Because you see this in a lot of other disciplines. And how would you recommend that people handle the large data problems around the bioinformatics? And we have the large data problems in other disciplines as well.
So for the community that I'm supporting, they're mostly not optimizing for speed in a way that would require a more sophisticated language. So actually, I support a lot of people who are writing their code in Perl, R, and Python, and just the standard, scaling that up, but not, using some of the parallelization or more advanced libraries, but not languages that are more esoteric than that.
Yeah, I'm in a kind of a similar situation at Utah. We have several labs developing their own code, and they are really sophisticated labs with excellent software developers who are using every trick in the book to try to deal with large data volumes. But then there are beginning programmers who are trying to use R or Python for these things. And the issues that we run into there are things like memory management. So, when you're coding in R, for example, the onus is kind of on the programmer to keep track of how much memory are they using, to not overflow the memory that's on the machine. And so that becomes a user training issue that's quite a challenge.
And we will cover that later on in the call. So stay tuned. We have a couple of questions for Jana in the chat, but maybe we will let her answer those offline. And I will move to Mahmoud Mohammad Ishad from Harvard University, who I believe will be talking about Spark, but if not, then just talk about whatever you have prepared and we'll go from there.
Sure. Let me share my slides. I'm not used to talk without the slides. Okay, cool. So I work at FAS Research Computing in research software engineering team. I joined Harvard 3 years ago. My background is mechanical engineering, and I have been doing computational mechanics since my undergrad, working on simulating physical systems mostly. And then at research computing, we are working with different PIs, faculties, to develop software and data services to help them with their research. So being part of research computing is great because we have opportunity to work with different professional system engineers, software infrastructure engineers, people with background in like HPC. Basically, when we design the apps, the softwares, we make sure that it fits well in our infrastructure. So in terms of big data and big compute, I mean, first thing comes in mind is the infrastructure. So we are using CAN. This is Harvard's largest cluster with over 100,000 CPU cores, 500 terabytes of RAM. It has a decent amount of GPU cards, over 2.5 million CUDA cores. And you can see the stats for the jobs per year, over 29 million jobs per year. We are supporting over 500 labs and 5,500 users. So in research software engineering, we work with researchers to develop scientific software and data services, and also designing the system for those projects. We also offer consultation and training. So far we have a few staff, and we are hiring for more like data engineers or developers in coming weeks. To support any like big data, big compute solutions, as I said, infrastructure plays an important role. So we offer high performance file systems, Lustre file system with combined 56 gigabytes per second read and write, and some flash file system for some high I/O machine learning and AI application. If you want to update the hyperparameters faster. And also we have different InfiniBand configuration on compute nodes. The new hardware that we are getting, they are all HDR that gives 200 gigabit per second connection between the nodes. If you are writing like a data intensive application, and you, let's say an MPI application, and you need to two nodes talk over an internal network, that provides the infrastructure. As I said, there is like 100,000 CPU cores, and we have public queues. Any faculty can buy their gears, but they will be added to the public queue. If they are not using it, other researchers can use them. So I have seen users using 10,000, more than 10,000, sometimes more than that, 30,000 cores for their job. And if they need reservation, let's say, for example, for COVID-related research, they can, with approval, we can create reservation for them so they can do their big compute jobs. And in data science and research facilitation team, which Raminder is leading that group, they also work with researchers to design their workflow. If anyone wants to move to cluster and they are not sure what application they are using, what application they should use, they work with them to design it. And in my team, we develop those apps and work with researchers for that. A few projects, we work with Center for Brain Science, a lab in Center for Brain Science. The first project was high throughput animal behavioral research, where over 200 boxes are generating data for each animal, and consists of videos, audio files, recorded any hardware activity in the box. And they are shipped to Canon on Lustre file system, and they do a lot of machine learning and AI on those data. The other project that we are currently working is recording from the brain, which yields a terabyte per animal. and we are doing MPI basically on the cluster to make the code parallel, and it can scale on any number of nodes. The other project that we are working with School of Public Health, they receive data from different sources, air pollution, census, health data, and they come in flat files or either through API, for example, census, and we are using Apache Airflow. We are designing Apache Airflow to create those processing pipelines going from the flat files to the database. And also when the users request portion of the data, that also can coordinate the extraction from the database and putting in the compute space where they can run our code or Python codes. The other project that Raminder did with a group in SEAS, School of Engineering, with David Parks. So he worked on Elasticsearch. The data was coming from different resources, NetFlow, JSON, and emails, the body of the emails, and basically feeding them into Elasticsearch in order to do NLP type of analysis, and using a Spark for the interactive data processing. And for the analysis side, they use RStudio, Jupyter for that. So for this project, Raminder designed like a customized workflow and purchased hardware specific for that project. So in terms of data operation, from the data transfer, we have Globus. I know many schools have it. So they can either coordinate the transfer by the code or just through the web interface. Storing the data in our infrastructure, they can go with SQL or NoSQL options. And they can use a Spark for Hadoop. I don't think we have an actual implementation because we don't support HDFS, but we can mimic that by using high performance network file storage. And there is like a wrapper to do that. And from modeling, visualization, and services like a Starfish, we use for data management. And we have deployed on some big file system over petabyte. And researcher can go and see insights about their data stored, or Kibana for visualization of any, let's say, Elasticsearch database that we have. Yeah, that's it. Workflow design, optimization, or if it's development, then they come to my team. I would be happy to answer any question.
All right, I have one question with respect to the data transfer. What we do here at Utah is that we have dedicated data transfer nodes that bypass the campus firewalls, which we find very important in getting the good transfer speeds to sites of the university. Do you guys do something like that as well?
We dedicated 4 data transfer nodes, one in both of data centers, in Boston and in Holyoke in Massachusetts, to coordinate the data transfers. So but depending on where your data are sitting in our data center, you can use one of them. Yeah.
Okay, awesome. Then we have one question that is not technical, and that is the audience is curious about the sounds behind you, if it's either a bird or a guinea pig.
Sorry, this is my cockatiel,
okay,
my parrot.
Okay.
Yeah, I plan to stay with them, but maybe it was not a good choice to leave them behind.
It's okay. Let's have some enjoyment among the people.
Cool. Let me stop the presentation.
We also, there is one thing from Scott, which actually kind of relates a little bit to what we've been talking about, and that is how they serve packages through, and that is the VMFS through the Compute Canada. So just take a look at the link there. I found it intriguing last year at PERC, and still kind of looking into ways how we can set it up over here. It's a good way how to share applications. Let's see, we have a couple more minutes. So maybe I'll ask one more question from Nelly, and that is, how do you find customers that have the big data projects willing to work with you, but not their graduate students? I guess I'm not quite sure what that means. But anyway, maybe just say how do you work with people that have big data? How's your processes on onboarding? I suppose.
Could you?
Yeah. So when you have people with big data projects, how do you work with them on board?
Yeah. So I can give you an example. We had from an external collaborator working with Harvard faculty. It was using like analyzing different user data, and he was looking on some Spark application. Most of the times, they don't have a proper problem statement. They know what they are trying to achieve, but just learning what they really need takes, like, we usually schedule like a meeting with them, consultation, going over the details, what they're trying to do, and see what is best fitting their the resources we have and what they have on the cluster. Some labs, for example, have storage on Lustre file systems. Some of them have on Isilon. Or where that data is coming from. Is it through flat file system? Is it through API? Do they need to set up a VM to serve? So basically, by a few consultations, we work with them to design the system and the solution they want.
All right, great. Okay, so now let's move on to the programming part of our discussion, and then we'll start with Chris Myers from Cornell University, giving us some ideas about how to optimize Python for big data.
Unmute myself. Sorry, can you see my screen, or is it the blank screen? I'm trying to figure out where my stuff is.
It's the blank one.
The blank one. Okay, so let me go back over here. Sorry about that. Always a challenge. Okay. I won't bother putting it in slideshow mode so that it doesn't try to do that. Okay, so right. So I want to talk a little bit about Python and sort of how to think about working on big problems. I guess I'm going to tilt a bit more towards the big compute end of things than the big data end of things, but of course they're very much related. So I mean, Python is a very popular language for scientific computing, and not just for, I mean, certainly for people getting started out, but also for people who are very, you know, doing very advanced and high performance kinds of work. And I think this is both because it's a, you know, it's recognized as a very expressive language, but also that there's this very rich ecosystem of tools that have been developed over many years. I mean, the scientific computing community was really a very early adopter of Python once it was, you know, being developed in the early 90s. But Python is an interpreted language, and so it's slower than equivalent compile codes. And so part of what I've been trying to, you know, or a number of people have been working on is, you know, how can we get the best of both worlds? How can we get this both expressiveness and performance? If there are trade-offs among these things, where are they? How can they be mitigated? How can we best, you know, build programs to manage big compute and big data? So, I mean, like most, if not all interpreted languages, Python has a way of communicating with compiled modules. So there's a Python C API that's defined to work with the default C Python interpreter. And even though Python itself was not developed as a technical programming language, this interface to compile code has been from the very beginning, you know, really leveraged in a number of very useful and creative ways. And so what I'm sort of depicting here are sort of three axes along which we can try to get better performance in Python code. One is to get more of our computation running in these compiled extension modules that are communicating with the interpreter through this API. Another, of course, is running multiple processes in parallel. And then there are a number of tricks, you know, that people have recognized for getting sort of faster native Python when you're not going one of these other routes. So as I said, there's this rich ecosystem, and I'm not going to go through everything on this page here. It's really just to sort of show that I mean, this is a big community that's been developing a lot of very useful tools over many years for numerical and scientific computing and visualization, for machine learning, especially rather recently, for managing data and dealing with big data problems, for frameworks for compiling parts of Python code and generating these extension modules, as well as libraries for supporting multiprocessing in various ways. And one of the things I want to make note of here with this ecosystem is it really is kind of all tied together pretty well. That NumPy is this sort of a cornerstone of a lot of this, where these other packages are then built on top of the basic array functionality that NumPy provides, but then adds additional things. So a lot of these tools kind of work together because they use a lot of the same underlying kinds of data structures, and so you can sort of move easily from one to another, depending on your application space. So there's sort of a variety of tools and strategies that have been developed to support this kind of performance enhancement. There's a lot of work that's been done on developing compile libraries. So these are, things that libraries that are written in compile code, but that can communicate with the Python interpreter through the Python C API. And basically there, what we end up doing is aggregating a lot of computation. Instead of doing a lot of back and forth between the interpreter and a compile extension module, you sort of aggregate big chunks of computations, so that you're not paying a lot of overhead for this kind of communication. More recently, there's been a lot of interest in trying to develop, well, I should say, I mean, it's been going on for a while in various projects, various ways of compiling parts of Python code so that essentially these extension modules get generated for you. So Numba is a project and a set of tools that does some just-in-time compilation with really minimal kinds of code changes, and is very useful. Sort of, whereas if we're using something like NumPy to compute something with these large data aggregations, Numba kind of encourages us to unroll all these loops that we've done away with, and then sort of throw compilation, compilers at it to optimize, and that can actually be very powerful. Cython is something that's been around for a while, which actually allows extensions beyond Python in the form of type declarations, but with that additional information, the Cython compiler can then generate very efficient, compiled code that can be called from within Python. And then there's a number of tools that have been developed over the years that allow one to take an existing code base and sort of parse, function and class declarations and things, and sort of generate all this API interface code for you automatically, so that these libraries or programs can be called from within Python. And then there's various tools that have been developed to support concurrency and parallelism. So one thing it's noting is that Python, the CPython interpreter has a global interpreter lock. So even if you write sort of what you would think of as multi-threaded code, only one thread that's interacting with the interpreter is going to run at a time. So that is something that people have run up against and have been trying to find ways around. There are multi-processing approaches where instead of working at the level of threads, you're working at the level of processes that are more heavyweight, but that allow for concurrency. And then there's various wrappers around things like the MPI libraries and OpenMP that allow for parallel execution. It's worth noting that a number of these things, there's increasing amounts of support for multi-threading on multi-core machines, really without much need for reprogramming. So for example, NumPy links to BLAS and LAPACK, and so if you're using something like the Intel MKL, which provides optimized versions of those libraries, you can basically just set environment variables that say how many threads you want to use, and all of that sort of multi-threaded code which is not subject to this global interpreter lock can run again just by responding to an environment variable being set. And similarly, both Numba and Cython allow for some parallel execution that you don't explicitly need to build into your own code. There are a number of sort of tips and tricks and caveats. I mean, there's lots of different ways of approaching these kinds of problems, as I was sort of alluding to. There's not one solution that works for all use cases, but there are lots of options. But you kind of need to understand, what is it you're trying to achieve, and how can you best sort of optimize that. This landscape of tools is constantly changing, so it's good to understand the underlying principles of infrastructure, understand what this API consists of and how tools can leverage it, rather than necessarily being tied to any particular tool. There's a lot of useful tools for empirical performance assessment, which is really crucial for getting information about timing and profiling and memory usage. Obviously, there's a lot of interest in using Jupyter notebooks, and for some people, that is sort of how they use Python, is in Jupyter notebooks. But this is not necessarily the best environment for doing high performance computing. And so I think part of what we need to do as a community is to teach people how to run, write and run Python programs on the command line so that they can make better use of HPC resources. There are lots of issues with dependencies and versioning compatibilities among all these different interacting packages. So it's important to make use of either virtual environments or some of the module infrastructure on clusters to manage these installations. And then it's also, we were talking, there was some discussion earlier about memory management. I mean, NumPy provides this very nice interface, this high-level array syntax that lets you write very compact code that does all these aggregate operations on arrays, but often those suffer from the proliferation of temporary arrays, which can both impact, memory footprints as well as runtime performance. But some of these compiler-based tools that might be able to actually provide better performance with smaller memory footprints by avoiding some of that temporary array creation. So just to close up, I mean, I've been developing. So at Cornell, we have this CVW, the Cornell Virtual Workshop, which is a big collection of different topics different topics in computing and programming and high performance computing. And so I've been developing a few things on Python for high performance and using Python for various problems in data science. I've previously developed a graduate physics course at Cornell that uses Python to address a lot of different sort of problems in science and engineering and biology and like. And if you're interested in sort of explicitly in kinds of big data frameworks like PySpark, the group at Pittsburgh has developed a very nice workshop that's run through Exceed that runs recurrently that gives a very nice, sort of 2-day introduction into how to use things like PySpark and TensorFlow for big data problems. So I'd be happy to answer any questions about any of that.
Okay, thanks. We'll probably have to keep moving to Katya because we are very short on time. So there are a couple of questions in the chat that I'd appreciate if Chris, you could answer. And I definitely give a plug for your virtual workshops. They are awesome and we use them with our users all the time. So
great,
please do that when you have a chance. And with that, I'll hand the mic to Katya, who's gonna, from Boston University, who's gonna tell us something about her experiences with R.
Hi, everyone. My name is Katya Bulyakova from Boston University. One thing that I wanted to say before I shortly do my presentation is that this talk actually was designed to give you a very brief overview of topics that we wanted to figure out if there's an interest or larger interest in those topics. So if you are interested in any of the topics that you heard today, we would like to hear from you, and then we will dedicate a whole hour of the whole session so we could get more details and ask more questions. With this, I will start my very little presentation about high performance computing in R. And I can talk about that for a few hours, but here I'll try to manage to put it into 5 minutes. So we work at Boston University, we work with more than 3,500 of researchers, and quite a few of them, especially those who work with R, are in bioinformatics, some in math and statistics and earth and environment, but the first thing they do, they read the data. And the way you read the data, you use read.table function in R. However, there are a number of options. You can add arguments to that function. You can use read_table function from the package read_r and also utilize some options to it. And you can use my favorite fread function in library data.table. So what does it give to you? So here is a little table, and in this case, I actually read a tiny file, which is like 164 megabyte, but I'm comparing speed up you get with this option. You can see the difference between reading it using the default function read.table and other options is great. So when you really work with a very large file, like the one that I worked with, one researcher took more than half an hour to read using read.table. If you use, say, fread, and at that time there was no parallelization yet available for that function, it still allowed us to finish it 10 times faster. And nowadays, F-READ provides an ability to do it with multiple threads, so you can increase, you can improve the time even better. Once you read the data, you need to do something with that. And the worst bottleneck that I see with over and over again is when people grow their vectors and matrices. They would start with an empty vector, and then somewhere in the loop, they would add a new calculated element to their array. And here I'm doing it for relatively small, I would say medium size of a vector. And as you can see, not only the time to do that very, very trivial operation, the total time is huge, but also significant system time. So that's one of the first things I tell my users. And they tell me, oh, R loops are bad. That's what they read on internet, that R loops are very, very bad. And I would like to defend a little bit. Yes, of course, R interpreted language and loops are not good there. But if you do allocate memory first and then use the same bad loop to fill that vector with a new value that you want to put there, you can see there's not even significant amount of system time detected at all, and the elapsed time is many, many hundreds or 1,000 times faster. So that's one of the first things I teach people when I work with them, our researchers. The same happens, of course, with matrices and data frames, starting with the null matrices and then using R-bind function within a loop is very, very slow. Again, you allocate memory and then you fill in the matrix. Another bottleneck, especially in bioinformatics, for whatever need, they very often either generate random numbers or they sample from some large vector. And the way it's done, for every observation they have, they would either sample or create a normal, a random number, and then they would proceed with whatever they need to do. Much, much faster, and it's, as I said, it's not just some percentage of times faster, it's significant amount of time. If you create those random numbers or sample it before, and then you would use those generated numbers in the loop, that would make application run significantly faster. And of course, another thing that very few people are aware of are the difference between data frames and matrices. Very often in bioinformatics applications, data frames contain elements of the same type, like all numeric and all character values, and then they would access those elements rows by row. And as you can see on this slide, yes, if you access data frames and matrices column-wise, data frames are great for that. You, like for the example that I created here, it's data frames work 35 times faster. But if you do need to access your data using rows, you will get a huge slowdown. So if your data, again, if you access your data by row, if you use, if the data are the same type, you should use matrices. And the same applies to creating matrices and data frames, right? When you just creating a single column in matrix and data frames, for matrices, it's 10 times faster than a data frame.
Hey, Katya, I'm very sorry to interrupt here, but we've just got 2 minutes left. Can you finish up in a minute? Great.
Yes, I'll try to do it in a limit. So you should look at the help function of and make sure that it's optimized using RCPP, and sometimes parallelizing using GPUs helps, like in a recent project, applying all these techniques and calling things from writing CUDA kernel allowed me to speed up application written initially in R 200,000, more than 200,000 faster. And of course, there are different techniques in using parallelization in terms of memory management and speed up of your code. And I'll be happy to share this in more details.
Thank you, Katya. Wow, that speed up is awesome. I have questions. That's exciting. So I'm just going to go ahead and invite everybody to sign in if you haven't done so before. The link is in the chat for that. And just as a reminder, this call was recorded and this recording will be up soon. The post-call email will include information about where to find the recording and the slides. Today's topic was big data, big compute solutions. So thanks to our speakers today, Brett Milash, Mohammed Shad, Chris Myers, Katya, and our moderator, Martin Kuma. And thanks also to Bob for helping get us underway. We have a number of rich topics coming up. In August, we'll be having an all-people network call on the condo model, and I am very excited about that one. We're also planning on having our now annual PERC recap call on August 13th. So be sure and go to PERC and then we can all talk about it when we come back. More information about the dates on those will be coming out via email. If you have any call topic suggestions, please add them to the future call topics document. The link to that is in today's call document. And I just want to thank everybody who worked on the call. So that's Claire and Christina Wirwan, Martin and Lee, Amy, Katya, Bob, and I'm Jana Nugent. Thank you for joining us today. See you at PERC and see you in August.
Thank you.